Salam and a very good day to Dr. Hamdan bin Muhammad Yusuf. We are from Group 17, Nafran Sinti and Berhad, would like to present about our integrated design project. Myself, Kavnishna Dr. of Subramaniam with matrix number 1958 and 37, and my fellow group mates who are Chongwan Singh with matrix number 198328, Nur Maisara bin Tiramli with matrix number 1963 and 09, Muhammad Salihin bin Muhammad Hitsif with matrix number 199030. Let us brief about what we are going to present throughout this presentation. It is about the process flow diagram, Aspen simulation and manual calculation comparison, recycle stream, unit operation design, safety analysis, costing analysis, conclusion, and our recommendation. Let me introduce about our project. Our project is to produce 99.9% of purity from the naphtha which is fed with 500 ton per year. However, our production has become 43,944 ton per year of ethylene. Yet, this is a non-profitable in this current market due to the price of naphtha and ethylene. We faced a biggest loss which is 99.52 of maximum loss and 97.94 with minimum loss. Let me explain about the process flow of this plant. The naphtha is fed into the heater to heat it to the furnace temperature. In the furnace, the naphtha is cracked and the light hydrocarbon produced will be cooled and then remove the water. Demethanizer, deethanizer, and depropanizer is used to remove methane, ethane, and propylene respectively. CO2 splitter is used to split the ethane and ethylene, and finally 99.9% purity of ethylene is produced.
Hi, my name is Nur Maisara and my matrix number is 196309. I will be presenting the Aspen comparison, and I will start from the first unit, which is heater 1. So the heater 1 is used to preheat the naphtha to change its phase from liquid to gaseous. So we will look at the table of the Aspen comparison here. Most of it are similar from the input temperature and the mole flow rate. The difference is the output temperature for manual calculation is 889 Kelvin, while for Aspen simulation is 1097 Kelvin. For the pressure in the manual calculation, the input is 2.665 atm and the output is 5.8. Meanwhile, for the Aspen simulation, it remains constant at 4.9 from input to output. So the major difference is at the energy, which for manual calculation is 30228 and Aspen simulation is 44265 kilowatt. So the difference is not that big, but it is the difference majorly is because of the difference in the outlet temperature, which causes the energy flow to be different. So next we will proceed with pump. Pump is used to increase the pressure of the water that will be used as steam in the furnace. From the table of Aspen comparison, everything is the same except for the pressure. Everything is the same except for the energy flow. As you can see in the energy flow, it has a huge difference. In the manual calculation, we have around 600 million kilowatt, while for Aspen simulation is only 11 kilowatt. So this is mainly due to the different method used for the calculation. As for the manual calculation, we use work done to as the energy flow, and the Aspen simulation is maybe more accurate than the manual calculation. So next we proceed with heater 2, which is used to increase the temperature of water at constant pressure to the furnace desired temperature. So the output from pump will goes into heater 2. So this is the water will be used in the furnace cracker to thermal crack the naphtha. So from the table, let's see again, the input is similar for both, but the output temperature is different, with manual calculation having 448 while Aspen simulation having 1097 Kelvin. For the pressure is similar and the mole flow rate also similar to the previous unit. And then we have the energy, which again is different with a big difference. For the manual calculation, we have 189,289 kilowatt. For Aspen simulation, 58885 kilowatt. So again, the difference in energy flow calculation might be to the difference outlet temperature, which causes the energy flow to have different numbers. Next, we proceed to furnace, where the main reaction occurs. So furnace is used to crack the preheated naphtha into ethylene and co-product. So in this furnace, we have two stream through input stream, which is the naphtha and then the water steam. So as you can see here, this is the chemical reaction and the fractional conversion, and the ratio of the steam added is 0.5 kg to the 1 kg of naphtha. So from the table, we will see that the input temperature for manual calculation is different for Aspen with 889 Kelvin, while for Aspen is 1097 Kelvin. And the pressure is from the output pressure for manual calculation is 5 mil, while for Aspen is 5.8 atm. And then for mole flow rate is quite similar with a little bit of difference with 4483 for manual calculation, while Aspen simulation 4453 kmol per hour. So we'll look at the energy flow, which has a very huge difference. This is positive for manual calculation, while for Aspen is negative. So the positive means that it's endothermic. So even though it has a huge difference, we assume that the manual calculation is valid because the reaction that occurs is supposed to consume a lot of energy, and it is supposed to be endothermic. So we believe that the manual calculation energy flow number is valid. However, the huge difference might be caused by the significant figure for molecular weight in the Aspen is much more bigger than manual calculation. Also, there is also the factor of temperature input and so on. So for my last unit is quench tower, which is used to lower the temperature of the products, leaving the furnace quicker to avoid more cracking and maintain the composition of the products. So what it does is basically cool down the product from the furnace to avoid it from further cracking. So from the table, the temperature and pressure is quite similar, and then for the flow rate is also quite similar from the previous unit. It doesn't have any difference. And then for the energy, as you can see in the energy, we have a large difference, but both has the same both are isothermic. So this is 84630 kilowatt, while for Aspen is 126329 kilowatt. We need to take into factor the difference is because of the might be because of the hydrogen and carbon monoxide that is neglected in the manual calculation. Also, the significant figures for the molecular weight in the Aspen is much bigger than in the manual calculation.
Hi everyone, my name is Zhongwen Singh and my metric number is 198328. So today I'm going to explain about the integrate design project that we did this sem. So I'm responsible for the Aspen simulation and manual calculation comparison, as well as the safety analysis. So let's move to the comparison. The first unit that I'm responsible is the adsorber. So the adsorber is used to remove the water from the stream, and zeolite 3A is used as an adsorbent in this unit. So this is the comparison. This is the manual comparison from Excel, and this is the information from the Aspen. So for the temperature, pressure, as well as the material balance is okay, in similar and okay. For energy balance, and also okay. Although three of them are 0, it's due to there are no energy change or anything involved, so we just consider 0, and it is acceptable because the Aspen, the total energy flow is also 0. For adsorber, we only consider the water change in the material balance because some of them are considered can be ignored because they are too little. For next unit is the demethanizer. So demethanizer is used in order to remove the methane from the other component. The recovery is 91% and the pressure, temperature as well as the material balance are okay. Just like what I say for the example as well, some of the components such as the hydrogen and the carbon monoxide is considered negligible. It is due to they are too little. You can see from the example here. It's too little in the flow rate, so we don't consider them. For the only problem here is the energy flow. Because we are using the wrong method, which is Antoine equation for our calculation for energy flow. So we have a very large constant in this unit. That's why the energy also is very big. That's why the big difference exists between the Excel and X1 calculation. And the same theory applying in the deethanizer. You see the energy has a very big difference. However, for the deethanizer, we have a very acceptable material balance and temperature pressure. So deethanizer is used in order to remove ethane and ethylene from the other component so that we can connect to the C2 splitter. So the propanizer and heater 3 is added because we want to add a recycle stream to recycle the component. So the propanizer it actually is used to remove the C3 component from other components so that we can recycle it. So here the same problem, the pressure, temperature as well as the material balance are okay and considered acceptable. Only the energy flow has a big difference due to the same thing that I said before, the wrong method is used. So heater 3 is used to increase the temperature so that it can meet the furnace desired temperature. Energy flow is okay, material balance also okay, temperature pressure also okay. So now we move to the safety C2 splitter. So C2 splitter is used in order to split ethylene and ethane. So because we want to produce 99.9 ethylene, so here is the comparison. Temperature and pressure are okay, material balance are okay as well because we only consider ethane and ethylene in this unit. Because other components are too little, so we don't consider them. For energy flow is kind of okay, although it is negative and it is positive because we're using the wrong method actually, but it's okay. So we move to the safety analysis.
Next, I will explain about the recycle stream. Recycle stream is basically a stream one where a portion of the outlet of the process is combined with the fresh feed and sent into the unit again. There are many reasons of recycle stream is introduced into a plant. Mainly is to increase the conversion of the reactant into product and for catalyst recovery and to dilute the stream and also to reuse the working fluid. The working fluid meant here is the lubricant or a refrigerant. Let us see the recycle stream process in this plant. The deethanizer bottom product is chosen to be recycled into the furnace. This bottom product is been chosen because of the component of butane, hexane and pentane, where it has been mentioned earlier that furnace will burn the butane. So it is reasonable to be choose the bottom product of deethanizer where the composition of butane itself is quite high. Two units being added between this recycle stream, which is depropanizer and heater. The reason of adding these two units are depropanizer basically to remove or to split the propylene. This is added to avoid the inner buildup in the system. Hence, the propylene will be splitted with the butane. However, the depropanizer outlet stream will be purged before it is introduced into the heater 3. Heater 3 basically is used to increase the temperature to the furnace desired temperature. Here, the table shows the Excel calculation for a recycled stream. Original flow rate refers to the flow rate of fresh naphtha from heater 1. Recycled flow rate refers to the flow rate of recycled stream from heater 3. Final run is the sum of original and recycled flow rate. Assumption run is the total inlet flow rate of furnace after recycling. Differences and difference square is basically the difference between the final run and the assumption run. This calculation is used solver, which is the calculation made in the Excel. The difference square is the total difference square is set to be 0 and the assumption flow rate is being calculated. Solver is used to calculate the recycled stream flow rate because solver will iterate the numbering before it being recycled into the furnace. Hence, the assumption flow rate mentioned here will be the total flow rate of the furnace after recycling has been done. So we can see the difference between before and after recycle is introduced into this plant, where stream 2 refers to the fresh feed, which is 832 kilomole per hour, and stream 2A refers to the flow rate of naphtha after recycling, which is 1432 kilomole per hour. Here we can see a huge difference, and we can increase the production of naphthalene into a 179 kilomole per hour. There is as I mentioned before, purging is done in this process. Purging is a process where the purge stream is a small blend off from a recycle loop to prevent the buildup of the inert and to remove impurity in the system. Hence, in this process, 50% of the recycled stream is purged, and accumulation of pentene and hexane can be avoided by purging, and the reaction inhibition by the impurities can be prevented. If not, the buildup will be hexane and pentene will be accumulated in the furnace and may cause the reaction to be inhibited. Next, we would like to compare the plant's process before and after recycling, and this are the effect of the recycle stream addition to the plant. Firstly, the total unit become decreased, which is from 18 units to 12, and the total C2 splitter used is also reduced, which is initially we used 8 C2 splitter and now we're only using 1 C2 splitter. And the naphtha flow rate, as mentioned before, is increased, and also the ethylene final flow rate also increased from 0.033 kilomole per hour to 179.45 kilomole per hour. The biggest achievement of this recycle stream is the ethylene production yield, where the 0.02% was the before recycling yield, and after recycling we got a total of 12.485% of yield.
Next, for the unit operation design part, the unit chosen is the C2 splitter distillation column, and this slide is mainly about the composition or the parameters of the material balance, which is we have the composition, temperature, flow rate, and also pressure for feed, distillate, and bottom. So mainly the feed composition, ethylene we have 50.1% and ethane 49.9%, while in distillate we have 99.9% of ethylene and 0.01% of ethane, while at the bottom we have composition of ethylene 0.01% and ethane 99.9%. Since at the bottom we have almost pure ethane, so we also sold ethane as our byproduct since it has high purity. Okay, next. Okay, so next is the steps to determine the number of stages by using the Metcalfe-Cell method, which is in this graph. So what we need to So what we need to do to obtain this graph is, firstly we need to plot a equilibrium line here, which is the curve 1, equilibrium curve, which is we can obtain the data, the equilibrium data, by using the TXY diagram. Okay, and then second, what we need to do is we plot a enriching line, and then Q line, and also the stripping line. So the number of stages is between the equilibrium line and the enriching and stripping line. Okay, so the parameters that we need are the F, or the feed, XF, XD, XWR, alpha, and Q line, which is F is the feed flow rate, which is 358.54. XF is 0.501, which is FF is the composition of ethylene in the feed, XD composition of ethylene in the distillate, and XW is composition of ethylene in water, which is 0.501, 0.999, 0.001 respectively. And then we need to have our reflux ratio, which is equivalent to 2.4, and then the relative volatility, or alpha, is equal to 1.97, and the Q line is 0.915. Okay, so from the calculation we get our top product flow rate and the bottom product flow rate by using the material balance, and we also get our L, V, L prime, V prime, QX, and what we need is the number of plate, including the reboiler, is obtained 43, and the feed plate from the top of the column 23, which means the feed is on the 23rd column. And then we have our minimum reflux ratio under 2.11077, and minimum number theoretical places, which is phase K 20.3729. Next, we have our design parameters, which is just like I said before, reflux ratio, number of theoretical plates, and feed plate number. And then this is the column dimension, which is we have area of 1.054 meter squared, column height 13.761 meter, and the diameter of 1.158 meter. And these are the plate parameters, which we have 22.04% of overall plate efficiency with sieve plate. Okay, and then this is the plate dimensions. Okay, these are the mechanical drawing based on the parameters that we have obtained before, which is the number of stages, the diameters, and then the number of holes. I forget to mention it. Okay, we have the number of holes is equal to 1198. Okay, so these are the holes, and these are the diameters, and then we have our number of stages, the height, and so on.
So for the safety analysis, for safety analysis, we can see that most of the chemical substances have a very low fire point and have a very high heat of combustion. So it is very high flammable and very dangerous. We can see from here, highly flammable, risk of injury, extremely flammable, and consider climate pollutant. High concentration of ethane can cause central nervous system, and we can conclude that most of the chemicals are highly flammable and explosive or maybe exposure to the high concentration of the chemical endanger the safety. So in order to prevent all of this from happening, we need to take some precaution. So the first precaution is the plant must be kept away from heat, of course. The second is we must be carry out the plant in a well-ventilated area so to prevent accumulation of high concentration of chemical. So the most important thing, of course, is the employee, which is us in the future. We need to wear some protective equipment such as safety goggles as well as a lab coat to protect ourselves. So maintenance of equipment also very important, and we need to install some gas detector so that we can detect, or the alarm can be detect the high concentration of chemicals so that we can fight it as well as possible, as soon as possible, and and make it to the safety level. So that's all from me. Thank you.
Assalamualaikum, my name is Nur Maisara and my matrix number is 196309. I will be presenting the economic analysis of the process design project, and firstly we will talk about the operating and capital cost. So we start by calculating the capital cost estimation. We have the fixed capital, working capital, and the total capital cost. Our fixed capital include the equipment costing, which we have 10 units, cost around $2 million. Our equipment consists of 1 pump, 2 heaters, 1 furnace, 4 distillation column, 1 quench tower, and 1 absorber. And the working capital is 20% of the fixed capital, so our capital cost is around $6 million. The rest of the capital costs are estimation except for the equipment cost. And then we have the operating cost. So our operating costs include the fixed cost and variable cost. So firstly, for the fixed cost, it is labor plus plant overhead plus laboratory, which costs around 1 million. This is an estimation from the fixed capital. And then we have the variable cost, which include raw materials and utilities. So for the raw materials, we have 3 raw materials used in this process, which is naphtha, zeolite, and coal. So for naphtha, we are required to feed around 500,000 tons per year. And the price for high demand is $200 million per year, and for low demand is $100 million per year. So the rest of the fixed cost is an estimation. So our operating cost is around 8.99053 times 10 to the power of $12 per year. Next, let's talk about the market demand of our main product from the process, which is ethylene. So for ethylene, this is the global market analysis, and it shows a linear increase in the trend. So for each year, it jumps around 3% to 4%. Next, we will talk about the cash flow of the company. Firstly, to improve the income of the company, we decided to sell our byproducts from the process. Ethylene is our main product, and our byproduct of the process is methane, ethane, and propylene. However, we are only able to sell methane and ethane because propylene did not achieve the lowest purity grade, which is 99%. Our production purity is only 97.8% for propylene. So as you can see here, this is the cumulative cash flow for our company for 20 years of production. In the first 2 years, we did not start the production yet, hence the negative cumulative cash flow. We started our production on the 3rd year of the production, and our operating costs exceed the sales of the company, hence the negative cash flow even after 20 years of production. So the company suffer from negative profit because the yield of possible product production is still low. Our ethylene production only have 12% yield, hence the negative profit. This is the graph of the cumulative cash flow with capital cost. As you can see, it is linearly decreasing, and we have a loss about $10,000 million per year, and it keeps increasing year by year. Hence, the production of the plant is not economically feasible.
Next, as the conclusion, the addition of recycle stream in the design increases the ethylene production as the final product. Next, some units in the plant need to be added or removed after the Aspen simulation session, such as pump and heater. Next, the different temperature, pressure, and flow rate of both manual calculation and Aspen simulation lead to the difference in the enthalpy flow and other parameters of the units. Next, the 99.9% desired purity of ethylene is obtained by the binary system of distillation in the C2 splitter unit. And lastly, the higher operating cost compared to the revenue, causing the negative profit value obtained. So, the recommendations are The byproducts with high purity, such as the methane and ethane, should be distilled and sold to avoid wastage and loss. Next, the working condition along with the mass and energy balance of the unit need to be revised to obtain the accurate and optimum condition with minimum energy required to save the cost. Next, the low yield of the ethylene in the C2 splitter can be increased by adding more recycle streams in the design. And lastly, the operating costs need to be minimized by using cheaper alternatives of materials and equipments in the design plan. So that's all from us. Thank you. Macam nak stop ni?